Hi, welcome back. It's Dr. Heath. We are getting started in Chapter 10 today. We're actually going to head straight into Section 10.2, but this whole chapter is all about data analysis and statistics. So Section 10.2 is all about the beginnings of displaying data. You will learn about categorical and numerical data, dot plots, stem and leaf plots, histograms and bar charts, and circle graphs. Okay, so what does data analysis mean? It's just an informal approach to statistics. It's a relatively new term used in math. Statistics, however, once referred to the numerical information about state or political territories. It comes from the Latin statisticus, meaning of the state. Today, statistics basically means making sense of data. Data are observations such as measurements, genders, survey responses that have been collected. Statisticians often collect data from small portions of a large group or sample in order to determine information about the group or about the population. This information is used to make conjectures about the entire group. Describing data frequently involves reading information from graphical displays, tables, lists, and so forth. So we have two different types of data that we first want to distinguish between. Categorical data are data that represent characteristics of objects or individuals in groups. So these could be black or white, inside, outside, students, non-students, parents, non-parents. But numerical data are collected on numerical variables. So in grade school, students may ask whether there's a difference in the distance that girls and boys can jump. The distance that's jumped is a numerical variable, and it's collected as numerical data. And this would also be things like heights or dollars are numerical data. So one way we can represent categorical variable data is through a pictograph. So for example, categorical data might be seen in determining the month that the most automobiles were sold. The month is the category, and then we use a symbol or icon to represent a quantity of those items. So in this case, on the pictograph, we use a symbol or an icon to represent a quantity, and the legend tells us what the symbol represents. So in this example here, we have a pictograph of the months and the number of newspapers that were recycled in weight. So each little stack represents 10 kilograms of recycled newspaper. So we could look at this pictograph and see that in July, there were 4 stacks of newspapers in the pictograph, so that represents 10 kilograms each, or 40 kilograms total of recycled newspapers in July. You can even see that September has a half of a stack, which would represent half of our key here, so 5 kilograms. So in September, there were 65 kilograms recycled of newspapers. We could represent the number of students in each teacher's 5th grade class at Hillview, and it's depicted with a tabular representation in the table and in the pictograph. So if we compare these two, we have Mr. or Miss Ames has 20 students in their class, and so if a little stick figure represents 5 students, to represent 20 students in Ames' class, we would have 4 stick figures, so 5, 10, 15, 20 students in Ames' class. Another way to organize numerical data now is with a dot plot. These are used usually when a group of data has less than 50 values. They get a little complicated and big if we have more than that. So if we think about students in Abel's class getting the following test scores. So here we have all of the test scores that students received in the class. We can create a dot plot by first starting with a horizontal number line, and then for each score in the set of data, we would denote it with a dot or an X above that corresponding number line value, and the number of X's above each score indicate how many times each score occurred. So we could take this and say, all right, well, one of the scores was 82, so I would mark on the number line above 82 with an X. So 80 is here, and so 82 will be 1, 2 up, because each tick mark represents 1. I would take an X and I would mark it above 82. And I would continue to do this for all of the values in my data set. So I could say, all right, the next value is 97. I need to have an X above 97. 70 is the next value. 72, 83, 75, 76, 84. So you'll see that some of these values are repeated. We have at least 2 values at 76. I think we actually have 3. So when we put these in our data set, we'll stack them above to show that there are 3 different data points at 76. So if we completed this, it would look something like all of these blue X's. So we can see how the scores among the 30 students were distributed. So we could just look at this table and say, all right, well, I can see 2 students scored to 72. 52 is potentially an outlier. It's pretty far away from the rest of our data. It's a pretty low score compared to the rest. Then we have kind of a gap between 88 and 97. No one scored in that range. We have the highest number of students scoring an 82, and then we have another little cluster around 97 and 98. So these are all things that you could say about these data. When it comes to dot plots and numerical data, we can talk about outliers, which are points whose value is significantly greater or less than other values, and we'll formally define this in our next lesson. But then a cluster is an isolated group of points. A gap is a large space between data points, and the mode is the data point that occurs most often. A stem and leaf plot is another way that we can represent numerical data. However, we are going to work vertically rather than with X's. So if we wanted to represent the scores for this class, again with a stem and leaf plot, a stem and leaf plot is going to start, we have a table, or just really we just need a vertical line. And we are going to decide on the stems that we want to use. So first I want to identify the high and low values of my data. So the lowest value is 52, and it looks like the highest value is a 98. So I need to have stems that are going to represent between 52 and 98. So I might have a stem for all of the values between that start with a 5 that are in the 50s, 60s, 70s, 80s, and 90s. So to construct a stem and leaf plot, I will use the second digit in my data set values as my leaves. So 52 was one number, so I would read this as the number 52. Then I would look for any values that are in the 60s, and I actually don't have any here. Then for 70s, we have quite a few values. So we have 70, 72, 75, 76, another 76, 73, 72, 76, 78, 77. So for all these values, I want to add my leaves. So I want to also add them in order from least to greatest. So I had 170, and then I don't have any 71s, but I have two 72s. I have 173. I have 175. I have three 76s, a 77, and a 78. I'm running out of room, but this is how I would go about constructing this stem and leaf plot. Once I complete it, I would get something that looks like this. And this stem and leaf plot helps us look at the distribution of the data, identify these gaps and potential outliers. In an ordered stem and leaf plot, the data are ordered from least to greatest on a given row, like I was trying to do. Advantages of stem and leaf plots is that they're pretty easy to create by hand. They are not super unmanageable when you have a large volume of data, and we don't lose any data values. We are representing every single data value on that stem and leaf plot. Some disadvantages is that we do lose some information. We know a data value exists, but we can't tell which one it is because there are potentially multiples of them. So to construct the stem and leaf plots, like I just illustrated, find the highs and low values of the data, decide on your stems, list the stems in a column from least to greatest, and then use each piece of data to create the leaves to the right of the stems on the appropriate rows. If the plot is going to be ordered, then list the leaves in order from least to greatest, and then add a legend identifying the values represented by the stems and the leaves. It's also helpful if you add a table, or a title, excuse me. Another way we can represent data, especially if we want to compare, is with a back-to-back stem and leaf plot. A back-to-back stem and leaf plot will have our stems in the center. Sorry about that. We will have our stems in the center of the back-to-back stem and leaf plot, and then we can read what values there are in each. So in this stem and leaf plot, we have on the left-hand side the second period class test scores, and on the right, the fifth period class test scores. So here, I can see that one student made a 50, a 5, and a 0 in second period. Another student made a 52. Someone made a 61, a 63, a 65, 72, 74, 75, etc. And then I could read the same values on the right. And then I can compare, see that generally there were some lower scores in second period than in fifth period. We might be interested in a problem like this to use a back-to-back stem and leaf plot. If we want to group the presidents from George Washington to Rutherford B. Hayes, so that would be from George Washington to Rutherford B. Hayes, and then from Garfield to Reagan. And we might want to compare their ages when they died to see if the first set of presidents lived longer or shorter lives than the rest of the presidents. So you could be asked to create a back-to-back stem and leaf plot of the two groups and see if there's a difference in their ages at death, and then maybe ask yourself which group of presidents seem to have lived longer. So the ages at death vary from anywhere between 46 to 93. I think that the president who died the youngest was JFK at 46, and then Ronald Reagan and several others also made it to 93, or maybe just one other, just Ford. So we need our stem and leaf plot to go from 40 to 96. So I would have 4, 5, 6, 7, 8, 9. And then I would group my first presidents, and my line is between Hayes and Garfield, the first 19 and the remaining 19 on this chart. And then I would add all of my data points. So I would say, okay, George Washington is 67, John Adams is 90. So this is the, well, let's put our earlier presidents. So George Washington was 67, John Adams was 90, Thomas Jefferson was 83, etc. And then I would add on my right-hand side, James Garfield lived to be 49, Chester Arthur 57, Grover Cleveland 71, and I would keep going in this way. So if we look at what this two-sided stem and leaf plot would look like, we can see that actually, surprisingly, the earlier presidents seem to be living a bit longer than the later presidents did. They had these ages on the higher end at death in about 70s, 90s, and those are coming from some of the earlier presidents, and some of the ages on the lower end are from the later presidents. And if we looked back at the 50s and 60s, they're roughly equal with when those presidents were dying in their 50s and 60s. So a stem and leaf plot shows how a wide range of values, it shows how wide the values of the data cover, where the values are concentrated, whether there's symmetry, gaps, and if data points are decidedly different from the rest of the data. So another way that we can represent data is with a frequency table, a grouped frequency table. So if we took that same data with the president's ages at their death, and we arranged a group frequency table using our ages at death ranging from 40 to 49, 50 to 59, etc., we could tally how many presidents fell into that range, and we could see that most presidents were dying around their 60s or 70s. So something to note about frequency tables is that each class interval needs to have the same size. The size of each interval can be computed by subtracting the lower endpoint from the higher endpoint and then adding 1. So 49 to 40 is actually capturing 10 years of ages, because we have 40 and then 41 up through 49. We know how many data values occur within a particular interval, but we don't know anything about the particular data values themselves. Like, we don't know which presidents the data values are representing. We don't know if they were one of the earlier presidents or one of the more recent presidents. So something else to note about frequency tables is that as we increase the size of our intervals, we lose more information. We can't identify as many gaps or clusters, and we need to make sure that all of the classes or intervals do not overlap. So histograms and bar graphs are other types of charts that are representative of our data. Histogram is made up of adjoining rectangles or bars. All the bars are the same width, and the scale on the vertical axis must be uniform. So it's actually pretty simple to transform a chart that tallies our data into a histogram with those equal sized intervals. A distinguishing feature between histograms and bar graphs is that on a bar graph, there's no specific order that needs to be taken, but there is order in a histogram. So a histogram is presented here to show that those ages of deaths of the presidents. So we have on the horizontal axis all of the ages that they died and then their frequencies. In a bar graph, however, we have spaces between the bars, and we usually use bar graphs to depict categorical data rather than numerical data. So here, if we wanted to look at all of these different students' heights, we can see Tom is about 145 centimeters tall, Mary is the tallest, and she's about 155 centimeters, etc. We could have placed these in any order. The order doesn't matter. Whereas with the histogram, we had a ordered number line on our x-axis. We can also use double bar graphs. So these are used to compare. If we wanted to go back to our presidential data and split it between later and earlier presidents, we could graph the frequencies of the decade of their age that they died in and represent the later presidents with green bars and the earlier presidents with blue bars. Other bar graphs, we can take a table and then represent that data with a percentage bar graph. So if we just have one single bar, and then we take the percentage of the data. So in this set of data, a teacher has asked their students what kind of shoes they were wearing. So one student was wearing dress shoes, 4 in flip-flops. And so we would take the total number of students that were surveyed. I believe this is 29 students, if I added correctly. 7 plus 3 is 10. 10 plus 14 is 24, plus 4 is 28, plus 1 is 29. So 1 out of 29, or 4%, were wearing dress shoes. 4 out of 29, or 14%, were wearing flip-flops. And so I would get the proportional length of my bar to show how many students were wearing which kinds of shoes. This table here shows expenditures for a business over a period of years. So between 1980 and 1989, they spent $795,000 on materials and $1.5 million on labor. And you can see that these prices are increasing in both categories for the materials and labor. But if we wanted to compare the proportions of their total expenses that were going towards material and labor, we could use a stacked bar graph. And so in this case, we have those ranges of years, and then all of the bars only go up to 100%. So even though there was more total spending in the later years, we are talking about just the total spending in each year. So even though the spending has increased, the split between labor and materials has stayed roughly the same. Another way to represent data is with a circle or a pie chart. It's only used to represent categorical data, and it's a circular region that's partitioned into disjoint sections, and each section represents a part of the whole. And the parts are proportional to the amount of data they're representing. So if we wanted to take this example on survival and death rates of the crew and passengers on the Titanic, we could create a circle graph for the survival group and a circle graph for the death group to make comparisons. So the entire circle will represent, if we look at the survivors, the 710 total people that survived on the Titanic. We will find the measure of the central angle of the sector that each piece of the pie will represent by making it proportional to the fraction or the percentage of the population that it's representing. So, for example, if we want to look at the passengers in first class who were survivors, they are 202 out of 710, or 28.5% of the circle should be representing the first class passengers. A circle has 360 interior degrees, so we should have 28.5% of 360 degrees devoted to first class. So 28.5%, we would do 0.285, that's 28.5% times 360. It should give us about 103 degrees of the circle. So we could do this for each of the categories of their survivors and calculate the approximate number of degrees the circle should represent. And then we could construct our two pie charts. So you would do the same thing for all of the people who died, but you can see here that in the survivors versus the people who died, there are a lot more people who, of the people who died, a lot more of them were crew or third class compared to the survivors. And you can look and see that these measures do align with the proportions. So like we said, the measure of the first class sector should be about 103 degrees, and it is on this protractor here. That is all for this section, and we will continue talking about data and their representations in the next lesson. Have a good one.